My name is Miss Macmillia Aripo. You are on to Akimo's Educational Online Services. I'm going to be your instructor for physics today on the topic machines, as we have on the board. And under this topic, we are going to be considering the following. We're going to look at a brief recap on work, energy, and power. Why? Because you cannot talk about machines without talking about the energy that is exerted actually for the operation of these machines. Alright, so we're going also to define machine in terms of work. By the time we'll be looking at this, you'll see why we need this, okay? We'll also be looking at the categories of machines and their examples, and then we'll also be looking at the terminologies associated with machines and the types of machines. This is where we're going to just pause for this topic. When we come back next time, we're going to now use what we'll be doing here to do some calculations. So please pay keen attention, because when you know how to know these formulas, if you can take hold of the formulas we'll be presenting here, by the time we'll be doing the calculations, you will not be left behind. Alright, we know very well that work is actually said to be done when the force that is applied on a part of a body or at a point moves its application by a distance. I say that again. When force is applied on a body, and this force that is applied on this body causes that body to change position or to move a certain distance, we actually say that work is done. Alright, and machines actually operate based on what? Application of forces. So when these forces are being applied on this machine, there is actually a change in the position of a body, and we know very well that energy is actually the ability to do work. That ability for you to do work is what we call energy. And power is the time rate of doing work. How much energy is expended per time in a given period of time. The amount of energy that is expended is what we call what? Power. Alright, having defined work, we are going to define machine. Very well, I know that when you were in your GSS, your junior classes or your primary school, you were told that a machine is actually any device that can help you to do work. Good. But now that you're doing physics, we are going to define machine in terms of work, not just a literal meaning. Actually, we say that a machine is actually a device in which when an effort is applied at one point of that device, it's able to actually overcome a resisting load at one point. Let me put that in diagram form to help you. If we have a device that is like this, let's call that device a machine, just like we have said, and there's an effort that is applied at this point of this device, and because of this effort that is applied, or this force, take note that this force, this effort is what? A force. Helps this device to overcome another force here, what we call the load. We can call this the load, and it's actually what? A resistance. So the force that is applied at one point of that device enables this device to overcome another force or a resisting force at the other end of that device. We say that that is machine. Definition of machine in terms of work. Alright, that will take us to the different categories of machines. We have two categories of machines. We have complex machines and we have simple machines. But for this topic, we are going to be dealing with the simple machines. And examples of these machines are your levers, your pulleys, your inclined plane, your hydraulic press. You also have your wedge and the likes of them. You're going to see more of them in the notes. Alright? We move on to terminologies that are associated with machines. Let's write them out. Terminologies associated with machine. We have, I want you to take note of this, the load, or let's start with the effort. We have the mechanical advantage. We use E for this, we use L for this, and we use MA for this. We also have the velocity ratio. We which is what? Your VR, and the last of them, but not the least, is your efficiency, which we use. You can use an egg that is inverted, or we use something that looks like this. So any one of them. What is actually the load? Like I said earlier on, when we're defining your machines, is actually what? Or let's start with the effort. It's actually that force that is applied to a machine to enable that machine to overcome a resistance. Okay, so your effort, which we use the alphabet E, is actually what? A force that is applied on a machine to enable it to overcome a resistance, or what we call the load. What is the load? It's actually that force or that resistance that is to be overcome. Let me say this. You have something to achieve or to accomplish, or what you want to say, a goal. If you have a goal in mind, definitely you know that you have to do some certain things to help you overcome, to help you achieve that goal. So liken that to your load and effort. Your load is actually that goal you want to accomplish, and then the effort is what your own input to achieve that goal. So you see that your effort is actually a force that you apply to that device to enable that device to overcome the load, which is what? A resistance that is on the way. Alright, we go to your mechanical advantage. What is the mechanical advantage? It is actually the ratio of the load to the effort. So we write this mechanical advantage equal to what? Load all over what? Effort. And being a ratio, take note of this, your effort is in Newton because it is a force. Also your load is what? In Newton because it is also what? A force. That means that when we have a force and a force as a ratio, it makes it to be what? Unitless, which therefore means that your mechanical advantage has no units. I don't want to ask you to calculate mechanical advantage and then you tell me 2 Newton, I will mark that wrong. So your mechanical advantage has no units. It is actually the ratio of what? The load to the effort. How about your velocity ratio? Actually, this is the ratio of the distance moved by effort to the distance moved by load. Do not confuse it. Whereas mechanical advantage is load to effort, your velocity ratio is actually the ratio of the distance moved by effort to the distance moved by load. So we say V dot R equal to what? Distance moved by effort all over the distance moved by load. Again, because distance moved by effort is in meters and your distance moved by load is in what? Meters. Your velocity ratio also has no units. Your velocity ratio is actually what? The distance moved by effort to the distance moved by load. Alright, let me say a few things for mechanical advantage and velocity ratio. Remember that your mechanical advantage depends on friction. In your SS1, we did friction. And for a body to actually move, the force that is applied, part of it is actually used to do what? To overcome friction. So you see that the effort that is being applied to a machine, part of it is used to actually overcome friction, and then part of it is used to raise the load. So your mechanical advantage, if the effort that is applied is smaller than the load, let's assume that you have mechanical advantage, your load is actually, let's say 2 Newton, and your effort is what? 1 Newton. What happens? 2 over 1 is going to be what? 2. Which means that if the effort is smaller than the load, the mechanical advantage is always greater than 1. And if the load is smaller than the effort that is applied to overcome it, the mechanical advantage will be less than 1. Whereas if the load is equal to the effort, the mechanical advantage is equal to 1. And this last option here can only happen when there is no friction. In an ideal machine, the mechanical advantage is always equal to 1. But you know very well that you cannot have an ideal machine in practice, because friction must actually take place for you to even have mechanical advantage. So when the load is greater than the effort, mechanical advantage is greater than 1. And when the load, the effort is actually bigger than or greater than the load, you have mechanical advantage less than 1. When they are equal, you have mechanical advantage equal to 1. Alright, the same thing, when you have an ideal machine, you will always have your mechanical advantage equal to your velocity ratio. And we move to the next part, which is what? The efficiency of the machine. The efficiency of a machine is actually defined as the useful work done by the machine. Is a ratio, actually, is a ratio of the useful work that is done by that machine all over the useful work that is put into the machine. Like I had said, because part of the effort that is applied to this machine is used to overcome friction, it therefore means that your effort is actually what? Friction plus what? Load. So part of the effort that is applied, some of it is used to do what? To overcome friction, and some of it is now used to raise the load. So this part that is used to overcome friction, of course, though is useful to the machine, but it's not very useful, because that's why sometimes you hear some things like noise in a moving part of the body. So we call that unuseful. That's why when we're defining efficiency, we say what? Useful work by machine. The useful work done by machine all over what? The useful work into machine. Or you can call this what? Work output all over what? Work input. And efficiency of a machine is always a percentage, and that's why we multiply this by what? 100%. So efficiency is given as what? Useful work done by machine, or what you call your work output all over what? The useful work into the machine, or what you call the work input, and it is always a percentage. So we multiply that by 1000%. Alright, that will now take us to details in types of machine. Yes, before I do that, there is always a relationship between your mechanical advantage, your velocity ratio, and efficiency of a machine. Let's do that before we go to types of machine. Remember, we have defined efficiency as what? Work output all over work input times what? 100%. When we define work, we said work is what? The product of what? Force times distance. Take note of that. So by the time we want to do this, let's say that our load is L, and then the distance moved by load is A. And then we have effort to be what? E. Again, distance moved by effort to be what? B. So let's go back to, and let's call this our equation 1. So if we do this, we're going to have efficiency to be equal to what? Work done, this is going to be L times A. That is the force, which is what? Load, times the distance moved by load, which we say let's call an A. Then all over what? The work input is what? The work you put, the force you put inside was your effort. So it is going to be what? Effort E times what? The distance moved by effort, which is what? AB times 100%. Alright, so also remember that we have defined a mechanical advantage as what? The ratio of your load to effort. So we are trying to see how we can make this This is our simple mathematics. We have L over E times what? A over B times what? 100%. We had already defined mechanical advantage as load over effort. So we can replace this by what? MA, mechanical advantage. So this equal to what? MA times. We also define a velocity ratio as what? The ratio of the distance moved by effort all over the distance moved by load. So what we have on the board is this is distance moved by load all over distance moved by effort, which means if you reciprocate that, you're going to have what? B1 all over B over A. Let me put that this way. Remember that you have 1 divided by B over A. It's the same thing as what? 1 times what? A over B. So you see, we have not changed this equation. We say that this, since we define velocity ratio as what? The ratio of the distance moved by effort to the distance moved by load. We can put this as a reciprocal of that. And this is what? Times 100%. So this means that we can replace this by our VA times what? 1 over VR times 100%. This will give us what? Efficiency equal to what? NA over VR times 100%. So many times you'll be told to find the relationship between efficiency, mechanical advantage, and velocity ratio. Take note of these equations, because in our next lesson, as we're going to divide this topic into 2 lessons, we're going to be using these equations to solve several examples. And that will now take us to what? Our types of machines. We have mentioned examples of simple machines, so let's look at them one after the other now. We mentioned the levers, the pulleys, we have an inclined plane, we have the screw, the wedge, the hydraulic press. Alright, and we have many other ones, okay? So looking at the levers, the lever is actually the simplest form of our simple machines. It actually works on the principles of moments. For the SS2 students who have done this, because this is an SS2 topic, we have already done moments. So the lever is an example of machine that works or operates with the principle of moment. It actually has 3 parts, which are what? The effort, the load, and the fulcrum. We had already defined the effort and load. The fulcrum here is actually the turning point of that machine. So if we have a machine, we have the load. This, another name for fulcrum is what? Pivot. That's the point where that machine turns, or what actually supports this machine for the load and the effort. We actually have 3 classes of levers. I'm going to give you a short way of identifying them. I want you to take note of this. FLE. FLE. Remember, we had said the lever had 3 parts: the fulcrum, the load, and the effort. So we have 3 classes of levers. We have the first class levers, we have the second class levers, and then we have the third class levers. For the first class lever, the fulcrum is between the load and the effort. So we have a fulcrum here, and if we have an effort here to overcome a load here, this type of machine where the fulcrum is between the effort and the load is called a first class order levers.
Take that part again.
I'm going to delete that. Did you lower your hair again?
Yeah.
Alright. Okay, we have 3 classes of levers. Or you may call it types of lever machines. Okay, I'm going to give you a simple acronym for that. Your FLE. The F here stands for what? The fulcrum. The L here stands for the load, and the E here stands for the effort. So when the fulcrum is between the effort and the load, that type of machine is called the first class order lever. Fulcrum between effort and load. Whereas when we have the load between the fulcrum and the effort, that is the second class. So we have this now. If this is your machine and you have the load in the middle, you have the fulcrum here and you have the effort here. This type of machine is called the second class order lever. Examples of the first class, before we come to this, you have your seesaw, which you played with in your nursery school. Your seesaw is an example of a first class order lever. You also have your scissors. The scissors you use at home is an example of a first class order lever. Even the pliers that several electricians and carpenters use is an example of your first class order lever. Then for your second class, you have your wheelbarrow. Remember that if you want to carry a wheelbarrow, you want to carry a load, the wheelbarrow is such that the effort is where you hold it, and then the load is always in the middle. Where the tire is actually your fulcrum point. So your wheelbarrow, your nut crackers, and your bottle top openers are examples of second class order levers. And then we also have the third class lever, where you have your effort between the fulcrum and the load. When you have the effort between the fulcrum and the load, that is your third class order levers. And a typical example of this is your fork, the fork you use in eating, and even your ice tongs. You know that you cannot easily pick eyes with your hands. So those tongs that are used to pick eyes are examples of your third class order levers. That takes us to the second type of machines. The pulleys. Your pulley is actually, a combination of, sometimes we call them the block and tackle system, where you have pulleys that are joined together. Okay, so if we have a pulley system that is joined like this, these are the pulleys that are connected. You pass a wire, depending, we have this, you pass a rope from here to the second, to the third, and then you connect it to what? An effort. Or rather, an effort. And this part of it is actually used to carry the load. So you see that this is tied to the load, and the rope that is used in connecting the four pulleys, now we have 1, 2, 3, 4 pulleys, is actually held. That's where the effort is being applied to actually lift a load. So these pulleys now actually helps us to know the velocity ratio of this pulley. So if you have 4 pulleys like this connected together to use in lifting a load, remember that the number of pulleys will determine the quantity of load you want to raise, you want to lift. So if you have these 4 pulleys now, you actually use this to determine the velocity ratio. You're going to have velocity ratio to be equal to what? 4. So this is very useful. We use this to know your velocity ratio. And of course, an ideal machine, your mechanical advantage is always what? The ratio of the load to the effort. Alright, so we go to what we call the incline plane. A typical example of this is when you want to, you know that on your own you cannot carry a drum of water. You cannot carry it. But if you can actually help yourself by using an incline. You take a plank, okay? Let's say you're living in a hilly region and you cannot carry that drum of water up. So you put an incline, okay? And the distance of this, the length of this incline is always your L. So let's say this is our load, your drum of water you want to push up there, okay? Remember, this is the ground level. And you're going to incline it at an angle, theta. And the distance of this point from the ground, let's call that our h. It is the height from the ground level. Why are we doing this? We want to also know how to determine our velocity ratio. It's easy to know your mechanical advantage because you know it's just the ratio of the load to the effort. But for your velocity ratio, it depends on the type of machine. Okay, for your velocity ratio here, you know that your VR, if you want to use, remember your trig ratios, where you have sine theta equal to what? Opposite over what? Hypotenuse. This is your opposite, h, all over what? Your hypotenuse is what? The L. But you know very well that your velocity ratio, as we defined earlier on, was what? Distance moved by effort all over distance moved by the load. Distance moved by effort all over distance moved by load. Remember that where is the distance? This is the distance, this load. The load was here and you're pushing it upwards. So by the time we get here, the distance it has moved is actually what? Your L. So this is going to be what? L over what? The distance moved by effort, whereas the distance moved by load is actually your H. Now if you relate equation 2, let's name them equation 1, VR. You see your equation 1, sine theta equal to what? H over L, and VR equal to what? L over H, which therefore means that the both of them are reciprocal. So you can say that your VR is equal to what? 1 all over what? L over H over L, which is the same thing as your 1 over what? Sine theta. So for your velocity ratio, we know that for you to find the velocity ratio of an inclined plane, you use what? 1 over sine theta. If you're given the angle, if you're not given the angle, you know that it's what? L over H. Are we together? Alright. And then we move to what? The next type of machine, which is the screw. You use it a lot. And a typical example of this is your nails. Okay, you know that your nails are threaded. Take note that the screw and the wedge are actually modifications of the inclined plane. They are adaptations from the inclined plane. So if you have your screw, you have this is what we call the number of teeth. This is used to form a circle, actually, and then okay. So we have a bigger screw, and then we also have a smaller one. So effort is applied on one to help to raise a load in another one, in the bigger one now. So they are arranged in this way so that effort is applied on this to help overcome a load. Okay, and for you to find your velocity ratio is actually okay for your gears. We're dealing with the gears for now. Okay, for your gears, we have the number of teeth. For you to know what your velocity ratio is, actually the ratio of the number of teeth in the driven wheel all over. Let me put that down. So let's say this is our driving wheel. Driven wheel. And this is our driving wheel. So it has two wheels, the driving wheel and the driven wheel. So you count the number of teeth here. These are the teeth. This. So the velocity ratio is actually the ratio of number of teeth in the driven wheel all over number of teeth in the driving wheel. Again, I say, for you to know your mechanical advantage, very simple. The ratio of your load to effort. It's only the velocity ratio that differ for different types of machines. So when you have your gears, the number of teeth, these are the teeth now, in the driven wheel all over, the number of teeth in the driving wheel gives you your velocity ratio. And then I was going to your screw. If you have a typical example, your bolt. Okay, let me just put these. Okay, now the difference between each of these threads is actually what we call, the distance from here to here is what we call P, and it is called the pitch. Alright, and remember that before it was threaded, it was actually a cylinder. And being a cylinder is going to have what? A radius. So your velocity ratio for your screw, example of this is your screw jack, which is used in lifting a car when you want to work on a car. So your velocity ratio is actually 2 pi r all over what? P. What is the r here? It's the radius of, remember that it was formerly a cylinder before shredded. And if it's a cylinder, definitely it has what? A radius. The cylinder is modified from a circle, so it has a radius, and that's what the R stands for. Whereas the P here is the pitch. The distance between each of these threads, they are always equal, and that's what we call the pitch. Okay, that takes us to your wedge. Example of your wedge is your axe. I know that for this generation you may not find an axe, but I know that you know how, you may have been told how an axe looks like, that is used in breaking your firewood. It has that sharp point, okay, that is used to cut through the wood. That is an example of your wedge. So we have this. You could see that it is inclined. That's why we say your wedges are typical examples, are modifications from your inclined plane. So you have the distance that this axe or this head moves into the wood. This is a wood that is to be broken. So we take note of this distance here, alright, and the depth it has actually entered. So we know that this is how we actually use to know our velocity ratio to be equal to the distance moved by what? Your distance moved by effort to the distance moved by load. Now, if this is your axe and you applied a force, the distance from, if this is the wood, it moved from, the axe head has moved from here to this point. That is the distance moved by the effort. And the distance moved by the load is actually the distance it has entered into the wood. That's how you find your velocity ratio. And then we go to the last of them, which is your hydraulic press. The hydraulic press, you see many cranes that are used in several companies in lifting very heavy bodies, because there are definitely loads that human energy cannot carry. So you see the crane using in carrying this load. So let's say we have two pistons in the hydraulic press, the smaller piston and the bigger piston. The load is always on the bigger piston, okay, and the effort, this is where the load is always kept, and this is where the effort is always applied. So you see that an effort is applied on this piston, which we always call the plunger. An effort is applied here. As this effort is being applied here, you notice that the load that was here begins to do what? Move up. You see that if you want to carry very heavy materials, let's say from the ground level of this building to the topmost floor, you know that you cannot carry it on your head. The hydraulic press is very useful here. All you need to do is to place the load on this bigger piston, and effort is applied on the smaller piston. As this is is done, it begins to elevate to where you want to lift it. So we see that these are several machines that are used in several companies. You can even construct one to use at home, okay? And take note of the principles that are behind all of these machines. This will bring us to the end of this class. For a comprehensive note, you're going to find it in the homepage of this platform. Alright, we talked about work, energy and power, because machines actually deal with what? Work. It is the force that is applied that enables it to do what? Overcome a load at one point. And today we're able to achieve a different definition of machines, different from what we were told in your nursery school and your junior JSS classes. Okay, and then we also looked at the different categories of machines, talking about the complex machines and the simple machines, and we're actually looking at simple machines, which we called out to be the levers, the pulleys and the rest of them. We looked at the terminologies there, the mechanical advantage, the velocity ratio, the efficiency, the load and the effort, to the terminologies that we always find in this topic called machines. And we had looked at the different types of machine and how to actually determine their velocity ratios. For your mechanical advantage, is simple, the ratio of the load to the effort. It's only the velocity ratio that differs for different types of machine. So I want to say thank you for listening. I believe that you have learned a few things from here. See you in our next lesson, where we're going to be using all these formulas, how to determine the different velocity ratios for different machines. We're going to be using them to solve problems. So go back and look at this again. You have your assignment where you're going to be drawing each of these machines. See that during the class I only did some sketches. You're going to be drawing these machines in your notes, and we're going to use them in our next class. Thank you for listening.